All right, let's go ahead and get started. Just to remind you guys, when is your homework number 2 / test review number 2 due? Tomorrow by 3:30. If you want to turn it in early, Katrina will take it in the back from you guys and stuff like that. By the way, Katrina, I've got a folder up here for you to help you organize that stuff too. All right, and so what are we doing today? Well, we're going to finish up section 2.8. There's a few problems from that. And then for the rest of the time, I thought I'd sit there and help you guys out with the web work problems from section 2.7 or 2.8 or whatever problem you guys want me to do. So just to remind you guys, last time we were doing two things. This is section 2.8. Differentials, which are used to help calculate or approximate, if you will, the change in some kind of y-coordinate. And the other thing we were doing was linear approximation to particular functions. Also, I want to remind you guys about, great, come by and see me. I'm more than happy to help you guys out. Also, we have so many other resources, the Math Resource Center. You can go there right across from the math department and get your particular questions, answer stuff. But I also want to emphasize the SI sessions. So please come to those SI sessions if you need help to get this material reinforced and stuff. You want to give us the times and of the SI sessions, just to remind everybody once again. I think I got them on the Canvas site. But let's write that down up here. I got a nice sheet of paper, and I'm recording this thing so people will be watching it from other classes as well. What time was it again? 3:30? 3:30 to 4:30. 12:30 to 1:30 on Wednesday. Okay. 5 to 6 on Thursday. And 3:30 to 4:30 on Friday. These are the times of the SI sessions. And what room was that in?
It kind of varies. You have to check the site.
Check the website for the room number, and I should have that actually on our Canvas site. Let's go back over here to our Canvas site right here. Go under modules, and right at the top where we have all that instrumental stuff. Let's see here, notes, supply list, prerequisite, I'll put it up here somewhere. Student support, access, on-campus learning opportunities, that's what I call it. Okay, there's the Math Resource Center times and what cover class they go. Here it is, the SI, here's information. So Tuesday from 3:30 to 4:30 is in Denny 202. Wednesdays from 12:30 to 1:30 is in Fretwell 118. Thursdays from 5 to 6 is in Denny 203. And Fridays from 3:30 to 4:30 is in Fretwell 202. So please, great places to also get some help with this stuff, because and again, why I'm going back and re-emphasizing the importance of the SI and the Math Resource Center and all these other areas, as well as coming by and seeing me or seeing Katrina during our office hours and stuff, is this is where students typically have trouble, is this 2.7, 2.8 kind of stuff. When we start putting it in a word problem format or asking strange questions about, these differentials and the change and whatever, and the linear approximation stuff. Which, remember, if you're asking for a linear approximation, if you get in trouble about the formula you're supposed to memorize, just find the equation with the tangent line. It's the same thing. All right, so. And we did a couple problems last time. The last problem we focused on, and I kind of rushed through it, but I got it completed, was this one right here. And I'm going to just kind of briefly go over this one because it's going to set us up for the web work problem that's next. It says use linearization techniques. Well, there's a clue to do this linearization equation stuff here, to approximate the square root of 16.1. Now, this is again where you actually have to come up with, because they're not going to give it to you, what the function is. Well, I'm trying to take the square root of 16.1, so my function is the square root of x, square root part. So you had to come up with that. And you always want A to be a good point that is near the point that you're trying to approximate. So what's a point that's very close to 16.1 that you can actually take the square root of? Yep, your good point was 16. So A would be equal to 16. The linearization equation that we all have memorized is L of x is equal to f of a plus f prime of a times x minus a. So I came over here, f of a is 16, so f is 16, square root of 16, which is 4. F prime of x is, remember this is square root of x, or x to the 1/2, so derivative is 1/2 x to negative 1/2, which is the same thing as 1 over 2 square roots of x. So f prime of a, f prime of 16 is 1 over 2 times the square root of 16, which is 1/8. So when I plug all this information in here, I get 4 for the f of 16 plus f prime, which I got 1/8, so I got 4 plus 1/8 times x minus your a, which is 16. This right here is my equation that would approximate the square root of x function near the good point 16. Since we didn't want to actually calculate the square root of 16, we want to use linear approximation. The square root of 16.1. Square root of 16.1 is approximately linearization of 16.1. So I plug 16.1 into my linearization equation. 4 plus 1/8, the same thing as 0.125 times 16.1 minus 16. 16.1 minus 16 is 0.1 times 0.125 is 0.0125 plus the 4, and that gave me the approximation of 4.0125. So instead of plugging numbers into crappy function, you can plug it into the linearization equation, and it will give you a close answer, approximate, but if approximate is good enough, then that's the way to go, because it's so much easier to plug things into a linear equation than it is to actually plug it into one of these interesting functions like cosine and sine, transcendental type stuff, or better yet, square root of x or whatever. So let's take a look at the next problem. This is a web work problem, and they're trying to mess you up because they're trying to get you to think. So here we go. The problem says this. Find the linear approximation of f of x equals the square root of 4 minus x at a equals 0, and use it to approximate the square root of 3.9, square root of 4.1. Again, this is one of these thinking problems, and I'll show you what's thinking in a second. First off, here's the deal. They gave me a function, f of x, which is the square root of 4 minus x, which is the same thing as 4 minus x to the 1/2 power. They want me to find the linearization equation. Linearization equation, which is L of x is equal to f of a plus f prime of a times x minus a. In this problem, a is equal to 0. So, what would f of a being equal to 0, f of 0 be? That would be the square root of 4 minus 0, which is the square root of 4, which is 2. The other thing I got to have is f prime of x. First off, as f of x is equal to 4 minus x to the 1/2 power, then f prime of x, what rule would I use to take derivative of this 4 minus x to the 1/2 power? Chain rule, derivative the outside, 1/2 pops out front. The inside 4 minus x stays the same, raised to the subtract 1, negative 1/2. Derivative the outside, inside stays the same, but times the derivative of the inside. Derivative of 4 is 0, minus derivative of x is 1. So that's 0 minus 1, which is negative 1. So when you clean this up, f prime of x is going to be negative 1 over 2 times the square root of 4 minus x. Now you got to be able to go from this to this. 0 minus 1 is negative 1. So negative 1 times 1/2 is negative 1/2. I got a function with a negative exponent. Negative exponent puts it on the bottom. So the 4 minus x is on the bottom, raised to the positive 1/2 power. But 1/2 power is a square root, so that's how I cleaned it up. Why? Because I want to calculate what f prime of 0 is. This will be negative 1 over 2 times the square root of 4 minus 0. That's negative 1 over 2 times the square root of 4. Square root of 4 is 2 times 2 is 4. The answer is negative 1/4. Does that make sense? So, my linearization equation, L of x is equal to f of a, which was 2, plus f prime of a, which is negative 1/4, times x minus a, and a was 0. So when I clean this thing up, I get L of x is equal to 2 minus x divided by 4. This is my linearization equation. But remember what the deal is. This linearization equation approximates the function f of x is equal to the square root of 4 minus x near a equals 0, near the 0 point. So as long as I plug in numbers near 0, I'm good to go. This equation right here will approximate this equation, which is kind of crappy to plug numbers in to. Now here's the deal. Here's the hard part. Does that make sense? So now we're going to use it. The first one is this. They wanted you to approximate the square root of 3.9. So what you've got to do here is you've got to figure out what x number I need to plug into, to be able to get the square root of 3.9. Remember, my function is the square root of 4 minus x. And basically, I want this thing to be the square root of 3.9. Can you figure this thing out and figure out what kind of x value you need to plug into this guy? Because the function is not normal. I mean, the last one was easy. I got the square root of x. I wanted the square root of 16.1. I plugged in 16.1 for x. What are you going to plug in for x here? Because the function is the square root of 4 minus x. What value of x, when I plug it in to this function, gives me the square root of 3.9? What does x have to be? 0.1. Why? Because what is 4 minus 0.1? 3.9, and then do we take the square root of it? X has got to be 0.1. So instead of plugging 0.1 into this function, what we're going to do is take that 0.1 and plug it into my linearization equation. For my linearization equation is 2 minus 1/4 x, and x is 0.1. All right, so this would be equal to 2 minus, you happen to know what 1/4 is in terms of a decimal? 0.25 times 0.1, which is equal to 2 minus 0.25, 0.025 actually. I'll just do it again, 0.1, which equals 2 minus 0.025. And what happens to be 2 minus 0.025? 1.975. So what is this telling me? This is telling me that the square root of 3.9 is approximately 1.975. We'll go back and check that in just a second. So instead of plugging it into this function, I plugged it into my linearization equation. Does that make sense? We got one more, and I didn't leave myself much room to do it, but I think we can handle it out here. Here we go. We also want to approximate the square root of 4.1. Since f of x is the square root of 4 minus x, what x number do you need to plug into the square root of 4 minus x to make it equal to this square root of 4.1? Very good, negative 0.1. So instead of plugging it into this function, what we're going to do is we're going to plug it into the linearization. L equals negative 0.1 would be equal to 2 minus 1/4 x, which is negative 0.1. So this is equal to 2 minus 0.25 times negative 0.1. A negative times a negative is a positive, so this is 2 plus 0.025, which makes it 2.025. And that square root of 4.1 is approximately 2.025. This is the linear approximation of that guy. Does that make sense? Now, of course, I'm going to confirm all this stuff with my calculator, but you guys get to use a calculator on this next test? No, so you better be good at this thing, man. All right, so here we go. What was the square root of 3.9? It was some crappy 1.974841766, but when we used our just linear approximation, we got 1.975, which is a pretty good approximation. Same idea here. What's the square root of 4.1? And the calculator tells me it's 2.0248485673. That's great. But when we did the linear approximation, I got 2.025 as it's rounded to 3 decimal places. So there we go. So it's a good approximation. But again, you had to outthink the problem because they gave you a weird function for this weird square root. So I put this problem on a test a few years ago. The reason why I'm telling you this is to scare you. And I had how many people mess this problem up? They got everybody, I would say 95% of the class got the linearization equation. But when I asked them to approximate the square root of 3.9, you know what they did? They plugged in 3.9 into the function. But the function was the square root of 4 minus x. So x is not 3.9 here. You've got to figure out what the x value is so that the function is the square root of 3.9. And they just plugged in 3.9 and got some weird crappy answer, which wasn't even close. And of all these people, like maybe 5% of the class actually got it right. And the rest of them, I asked them, well, why didn't you check it? You know, just think about it. What's the square root of 4? No, 2. So what do you think the square root of 3.9 is going to be? 12 point something? No. It's going to be slightly less than 2. I mean, the ability to look at answers and think about what you're doing with it. Does that make sense? All right. Here's another web work problem right here. Use linear approximation to approximate 2.001 to the 6th power as follows. The linearization L of x to f of x equals x to the 6th. So they gave me the function. We better write that down. F of x is equal to x to the 6th. They tell me my a number. My centering point is at 2. Can be written in the form of L of x equals mx plus b. What you're supposed to do on this problem, I think WebWork asked you what is m and what is b. So let's find our linearization equation. What is the formula for linearization equation? It is f of a plus f prime of a times x minus a. Got that memorized. So here we go. I got f of x. A is 2. So putting this together, f of 2 would be 2 to the 6th. What's 2 to the 6th power? Let's see if we can do some math in our head because we don't have calculators. 2 times 2, 4. Times 2 is 8. Times 2 is 16. Times 2 is 32. Times 2 more is 64. Oh, good. So f of 2 is equal to 64. Does that make sense? Now we need to know what f prime of x is. Well, don't hurt ourselves. What's the root of x to the 6th? 6x to the 5th. So f prime of 2 would end up being 6 times 2 to the 5th. This is 6 times, what's 2 to the 5th? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. What's 6 times 32? Uh-oh. Let's see here. Watch this. 32 times 6. That's right. I graduated 2nd grade. 6 times 2 is 12. Carry the 1. 6 times 3 is 18 plus 1 is 19. I got 192. Does that make sense? So f prime of 2 is 192. F prime of 2 is 64. So L of x is equal to, here we go, f of a, 64. Plus f prime of a, f prime of 2 is 192 times x minus a, which is 2. The problem here is this. There's my answer, but they wanted me to write this in the form of L of x is equal to mx plus b, right? If they were to write it in the form of L of x equals mx plus b, I need to distribute this thing and clean them up. So L of x is equal to 64 plus 192x minus 2 times 192, 2 times 2 is 4, 2 times 19 is what? 38, okay? So it's 383, agreed? And then I'm going to add subtract 64 from that, so let's come over here. Negative 384 plus 64. Basically, I'm subtracting. That would be 0. 8 minus 6 is 2. Carry the 3 down, and the bigger number keeps the sign. So what I get here is L of x is equal to 192x minus 320. Does that make sense? WebWork asked you, What's M and what is B? Well, you now tell me. What's M? That's right, the coefficient in front of the x, which is 192. And what's B? Very good. Sign goes with it. Negative 320. Good job. Does that make sense? Now, oh, what they want me to do? Oh, yeah. They wanted me to approximate. So here we go. But if I was going to approximate, I'm going to show you what to do. This is a great problem, but honestly, if I was going to approximate it, I would go back to this answer right here. I'll show you why. They wanted me to take 2.001 and raise it to the 6th power. So I'm going to do is my linear approximation, and since this linearization approximates the function x to the 6 at a equals 2, this will be the same thing as plugging in x equals 2.001 into my linearization equation. Now watch what I do. Instead of plugging in here, which will require me to do multiplication because I don't have a calculator, I'm going to plug it in here. 64 plus 192 times x is 2.001 minus 2. And this is the kind of math you can do without a calculator, order of operations. So this would be equal to 64 plus 192 times, what's 2.001 minus the 2? 0.001. What is 0.001 times 192? That would be 64 plus 0.192. Right? All you do is move the decimal place 1, 2, 3 places to the left here. 1, 2, 3. It's 0.192. And now don't hurt yourselves. But what's 64 plus 0.192? 64.192. And that is what approximately what 2.001 is to the 6th power. But of course, this is a web work problem, so I'm going to check it. Because if I was doing this by hand, I'd take 192 and multiply by 2.001 and subtract 320. I plug it into the function. Notice I get the exact same answer, but it was easier to do the math on the f of a plus f prime of a times x minus a rule. And now, so there's my answer, and let's just double check it. 2.001 raised to the 6th power. It's not going to be the exact same thing as this because it's approximation, but I'm expecting it to be very close. 64.1922416. There you go. If close is good enough for you, then approximation. Good way to go. Does that make sense? Did I lose you guys anywhere? One last problem, and then we'll do a bunch of web work problems for you guys. This one is also a web work problem. This is a web work problem from 2.8. But let's read the problem here. It says this. The edge of a cube was found to be 60 centimeters with a possible error of 0.5 centimeters. Use differentials to estimate A, the maximum possible error in the volume of a cube, B, the relative error in the volume of the cube, and C, the percentage error in the volume of the cube. All right, let me explain what the three things are. And two of them honestly have a formula, and I'll go over that. But here's the thing. The big deal is, number one, the maximum error in the volume of the cube. Use differentials to approximate this. All right, so here's the big deal. First things first. We're going to build ourselves a cube. What's a cube? It's a box with all sides being the same, right? So you've got a side here, and a side here, right? And we're going to build this box. And the sides are supposed to be built at 60 centimeters. 60 centimeters by 60 centimeters by 60 centimeters. Problem is, I'm building this thing out of wood. And if you ever worked in a woodworking shop, you know that that saw blade width could screw me up a little bit. Sometimes I have an undercut or sometimes I have an overcut, and that would create quote-unquote error. According to this problem, the error is what? 0.5 centimeters. My error, which is 0.5 centimeters. That's the area of my cut. So what exactly is this 0.5 centimeters? That is the maximum amount of change in S I can have. because we're talking about a side being 60 centimeters with the possible error being 0.5. So this is the error on the side. So in terms of differentials, remember, delta x is the same thing as, approximately the same thing as ds. So that tells me the ds is going to be 0.5 centimeters. I'm making a box, and I'm cutting this thing, and I could have at most, with the jaggedy little saw that I'm using, I can have a ½ centimeter off on the length. I could make this thing like 59.5 centimeters up to 60.5 centimeters the way I'm cutting the wood on these things. Does that make sense? So now let's use differentials. First thing you better know is we're talking about cube, and use this as the maximum by volume of cube. That word right there, volume, tells me what formula I should calculate. What is the volume of a cube? That's just something you should know from like junior high school. SAT test stuff. What's the volume of a cube? Side cube. Volume of box is length times width times height, but being it's a cube, all the sides are the same, so side by side by side, that's side cubed. Remember your formula for differential. So this is part A. The differential of volume would be the derivative of your volume equation times d, what the independent variable is. So my differential is going to be the derivative of the volume of a cube times d. What's the independent variable? Look at your volume. Volume equals side cube. What's the variable in this thing? Side. It's s. It's ds. Does that make sense? What is the derivative of the volume of a cube? What's the derivative of s cubed? 3s squared. And I'll put that over here just to let you know I did it. The derivative of v is 3s squared, and it goes right here. This is my differential. It's 3s squared ds. But now they want me to calculate it. This is the part A part. So my differential is going to be 3 times, what was s equal to? 60 centimeters squared times ds, and what was ds equal to? 0.5 centimeters. Does that make sense? So let's crunch this thing out. All right, big numbers, I'll use the calculator here. 3 times 60 squared times 0.5. I get 5,400. What would my units be? Centimeters cubed. Very good. It's going to have the same units as the original volume because this is approximating the change in volume. So please understand this. This is why error is bad. If I got a big old box out here that I'm trying to make, and that sucker is 60 centimeters by 60 centimeters by 60 centimeters, and I am at most a ½ centimeter off of my cuts when I'm actually slicing these sides up. What is the maximum error in my change in volume? What's approximately going to be the change in volume of this thing at most? 5,400 centimeters cubed. That right there sounds like an incredible amount of error. But well, one, it's volume. So every time you make a mistake, it cubes it. So I've really got some error going on here. Does that make sense? But this is why they ask you to put part B and part C in this problem. Because it does sound like a lot. And it, quote unquote, is, but it's not. Let me show you. Part B asks you, what is the relative error in the volume of a cube? Well, you got to know a formula here. So this is in your textbook in case you wanted to read along, but in case you didn't, here's the formula. Relative error is equal to the differential of the volume divided by the volume. You're basically doing a ratio of the change in volume over the volume. Does that make sense? So it puts it in terms of a percentage type thing. Well, it puts it into a decimal. And then part C, you'll actually change it to a percentage. Does that make sense? So, here's the deal. We just calculated the differential. What is the volume of this cube? Well, remember, it's side cubed. Well, what would the sides equal to? 60 centimeters cubed. So when you do that, that's going to be 60 cubed, which is 216,000 centimeters cubed. 216,000 centimeters cubed. So what would the relative error be? It's your differential, which we just calculated to be 5,400 centimeters cubed, divided by the original volume, 216,000 centimeters cubed. So let's do the math here. What's 5,400 divided by 216,000? I get 0.025. What would my units be on this 0.025? What are my units? Centimeters? Well, look at the formula. It is the differential of volume over volume. What were the units for the differential of volume? Centimeters cubed. What were the units for volume? Centimeters cubed. What's a centimeter cubed divided by a centimeter cube? Zero. It cancels. It's not zero, it's 1. This has no units because the units actually cancel. It was a trick question. Does that make sense? There are no units on this relative error stuff here. Does that make sense? So the answer that you would put in the blank on web work is 0.025. And of course, you got part C down here, and part C asks you, what is the percent error in the volume of the cube? Well, fine, I'll write it as a formula if you really want me to. Percentage error is equal to the differential of volume divided by volume times 100%. So what would that be? That would be 0.025 times 100%, and this would be what? What's 0.025 times 100%? 2.5%. Basically move the decimal 2 places to the right. As a percentage, you're going to get 2.5% of the entire volume of the box is how much error you could possibly create. Does that make sense? And 2.5% on the scheme of life is actually rather small. So even though these numbers look big, relatively speaking, they're small. It's at 2.5%. And that's why they want you to kind of do this problem, because sometimes when you're working these problems and you're getting these huge errors, you're thinking, oh my goodness, this thing's blowing up on me. Well, you've got to put it in perspective. And putting it into perspective means dividing it by the original volume to see what kind of percentage that thing turns into. That's the idea. Does that make sense? Did I lose you guys anywhere? And again, you got a Weber problem just like this one. All right, so what did I promise you guys? Instead of moving on and finish up chapter 3 and chapter 4, I decided to stop and actually do some web work problems for you guys. And this is the way I thought I'd do it. Kind of like the way Katrina and Sarah do it on the weekends, on Fridays when they're doing the review. So let me come over here to Canvas. Let me go to modules here. Now, let's look first at section 2.7 because there's probably lots of questions on that one. So I'm going to have to go through web work just like you guys do. Here's web work 2.7. I'm going to go log in on Canvas here, through Canvas. Here's web work. Which problem would you like me to do? And I've already done a... Okay, 13. Fine. Problem number 13. Yep, it's the kite problem. So I'm reading this problem, and I'm going to switch over to this page over here. This is problem number 13 on web work 2.7. What does it say? It said my problem, using my numbers, your numbers will change. A kite is 50 feet above the ground. Okay? So I got 50 feet above ground is my kite. Okay? The ground moves horizontally at a speed of, a kite 50 feet above the ground moves horizontally at a speed of 8 feet per second. So kite moves at 8 feet per second. Got it? Okay. At what rate is the angle between the string and the ground decreasing? What rate of angle between string and ground decreasing when 100 feet of string is out? When 150 feet of string is out. All right. So I've got all my information here. I'm going to go now and flip over to this so you can see. Classic word problem from a mathematician perspective. I skip over a bunch of words and I write down all the important numbers. Okay? 50 feet kite above the ground. So, and first thing, read problem, draw a picture, label it. I read problem, I'm going to draw the picture, label it. I've got a kite here. Okay? And I'm standing over here. The kite is what now? 50 feet above the ground. Now, here's the big deal. The wind is blowing and moving the kite, so I'm blowing here, and I'm moving the kite, so the kite is moving at 8 feet per second, which means I'm going to be letting out a lot more string to keep up with the kite, the fact that it's blowing this way, and keep going farther and farther away from myself. Does that make sense? And when that happens, the kite's going to be over here, and this angle is going to decrease. So that's how I knew the kite was blowing away from myself. Okay. What rate is the angle between the string, and I'll call this string right here in case you didn't know, and the ground? Here is the ground in case you didn't know. The angle between the string and the ground, I shall call him theta, because I've had enough math classes to know that all angles should be Greek letters. Okay? So this is theta, the angle between the string and the ground. So what are we looking for? At what rate is the angle between the string and the ground decreasing? I'm looking for d theta over dt. When there's 150 feet of string. Now, here's the big deal in this problem when you're doing it. You have to create variables for things that move. The 50 feet above the ground, this kite doesn't move. The distance from the ground to the kite doesn't move. The kite is actually moving, but it's moving relative to the ground. So I'm going to call the ground x. This will be the distance between the boy and the bottom of the kite. The other thing that's moving, since the kite was blowing this way, is the string. I'll have to be letting out more string. So I'm going to call string z as a variable. Does that make sense? And this guy right here, who is the 8 feet per second? Now look at the units, it's feet per second, which we know it is a derivative. But who's the derivative of who? Well, the big deal is he's the derivative of the kite moving away, right, this way. What variable moves away from the boy? X. So it's actually the dx over dt is equal to 8 feet per second, because it's not blowing up this way, it's moving, and they said in the problem, if you remember, horizontally. And the horizontal is my variable x. So 8 feet per second is dx dt. So we want to find d theta over dt when z, the string, is 150 feet. This is going to be a wonderful trig problem for us. Okay? Now, here's the thing. Here's how you have to do it. This is the easiest way. There's more than one way to do this problem. All right. I need an equation for this particular scenario, okay, that uses the variable that I'm trying to solve for. Remember, my goal is to find d theta over dt. So I have to have a formula that has theta in it and these other variables in it. Now, let's take a look at what we know. I know dx over dt. I know the derivative of x. So I make sure whatever equation I come up with has x in it, because I know the derivative of this guy. Question, though, is what do you know about z? Very little. I know I want to find d theta over dt when z equals 100. Well, that's awesome, dude. But do you know anything about z, especially the derivative of z? Do you know that guy? No, he wasn't given to me. So, in terms of coming up with my equation, I want to avoid the variables that I don't know much about. And I don't know much about z. I know much about x, but I don't know much about z. And I love constants because they don't move, right? So when I look at this problem, I want an equation that uses the angle, that uses the 50 feet constant, and that uses the x because I know about dx dt. This is the opposite and the adjacent, so what equation I want to use in trig? Tangent. The tangent of theta is equal to the opposite, which is 50, over the adjacent, which is x. This is my dude. Does that make sense? Now, what am I going to do to my equation? I'm going to take the derivative of this equation. Tangent of theta equals 50 over x. And I'm going to take the derivative with respect to time. But before I do that, I'm going to clean up, because of derivative purposes, 50 divided by x. You can clean that up. What's 50 divided by x also known as? 50x to the negative 1. He's going to be a little easier to take derivative of when in this form, because I really don't want to use quotient rule. So, here we go. Let's see what you've learned. What is the derivative of tangent with respect to t? Very good. Secant squared theta times, this is chain rule, d theta over dt. Every time you take a derivative of a variable, you got to tack on that d variable over dt. Equals, what's the derivative of 50x to the negative 1? That would be negative 50x to the negative 2 what? dx over dt. Every time you take a derivative of a variable, you got to tack on a d variable over dt. 50 was a constant. He held on. But this x negative 1 derivative, that would be negative 2x to the, negative 1x to the negative 2 times dx dt. And the negative 1 times the negative times the 50 makes the negative 50 here. Does that make sense? There it is. Now, let's clean this up. This is for your benefit. This is the secant squared of theta equals d theta over dt times, secant squared of theta d theta over dt equals negative 50x squared dx over dt. This would be negative 50 times dx over dt divided by, because it has a negative exponent, x squared. Now I'm going to try to help you guys out with this problem. What is the definition of secant? It's 1 over who? Secant is 1 over cosine. So secant squared is actually 1 over the cosine squared of theta times d theta over dt equals negative 50 dx over dt divided by x squared. Solving for d theta over dt, I get d theta over dt is equal to negative 50 times dx over dt times cosine of theta squared, I just wrote him like this, divided by x squared. And this is going to give me my guy. All I got to do now is plug in my numbers. Do you know what dx over dt is? Sure do. What is it? 8 feet per second. Do you know what theta is in this problem? No, I don't. Do you know what x is in this problem? No, I don't. I know I'm supposed to find d theta over dt when z equals 150. So what am I going to have to do? I go back and find these other two guys. Let me show you how. First thing, look at it. You've got x, you've got 50, and you've got z as the hypotenuse. What major theorem do you know that links all these guys together? Pythagorean theorem. So I'm going to use that. X squared plus 50 squared equals z squared. I'm supposed to find it when z is 150, so x squared plus 50 squared is equal to 150 squared. X squared plus 50 squared, I can do that in my head, but I'll type on calculator anyway. 2,500 equals 150 squared is 22,500. Now, what am I going to do to solve for x? Subtract 2,500 from both sides. And x squared is equal to, subtracting 2,500, gives me 20,000. And then I take the square root of that, and the square root of 20,000 is a crappy number. Okay, square root of 20,000. Yep. Is the square root of 20,000. Okay, fine. I actually got 141.42135562. I don't write out all those digits. I'm going to use that. Does that make sense? So I've got x now, and that's going to go here. You with me? The other thing I got to find is theta. How am I going to find theta? Well, here's the deal. Do you remember your equation? That the tangent of theta was equal to 50 over x. I now know what x is. What's x equal to? So the tangent of theta is equal to 50 over this x, which is the square root of 20,000. Question for you. Goes back, knowing your trig. What gets rid of a tangent so I can solve for the angle theta? Arctangent or tangent inverse. So I'm going to take the tangent inverse of both sides. This is inverse, arctangent, and this will cancel, give me with theta being equal to, and here it comes on the calculator, the tangent inverse of 50 divided by the square root of 20,000. And I get, and I'm going to, this is in radians, so I'm not going to round, I'm not going to cut around it, I'm not going to cut it off, I'm going to keep all the decimals. No rounding. 0.33983699095 is what I get. Does that make sense? Boom, 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 boom. Okay, so therefore, d theta over dt is equal to negative 50 times, oh yeah, what was dx over dt? You remember that one? Still up here, what is it? 8 feet per second times the cosine of 0.33983699095, close parentheses squared, cosine squared, over x. X was the square root of 20,000 squared. Does that make sense? Well, lose you guys anywhere. Questions? All right, let's type all this crap in our calculator. Here we go. So I get negative 50 times 8 times parentheses the cosine in radian mode of 0.33983699095. Close parentheses on the angle, close parentheses on the cosine squared, divided by parentheses the square root of 20,000, okay, close parentheses squared. Yes, I could have done that math in my head. Square and square root cancel. I'm dividing by 20,000. Does that make sense? But I'm showing you, I'm literally typing exactly what it is in the calculator. What do I get? I get, moving it up here, so you guys can read this, d theta over dt is equal to negative 0.01777778. What would my units be? This is why we love the Leibniz notation. What was the theta measured in? Radians. And what was time measured in? Seconds. There's my answer. But I got one more statement for you guys. Did I lose you guys anywhere on the application of trig in this problem? Does that make sense? But now, in terms of this problem, if we go back and look at the problem here, what answer, I'm going to get rid of this thing here. If a kite 50 feet above the ground moves horizontally at a speed of 8 feet per second, at what rate is the angle between the string and the ground decreasing when 150 string is out? What number are you going to put in this thing? Are you going to type in the negative 0.01777778 on this problem? No. Why? Because they said the word decreasing, right? With them saying the word decreasing, they're letting you know, yes, the kite's being pulled out, so my angle is going to have to be going down from where the little boy was sitting at. So if I type in this and submit answers, you know what the computer's going to tell me? It's wrong. My God, I did all this work for nothing. No, it's because of the negative. Because they said it was decreasing, I don't need the negative. So get rid of the negative, and then you get your UNC Charlotte Green. There you go. Does that make sense? Again, this is not math at this thing, whether you put the negative or not. It's an English game, whether you read the problem. Did it say it was decreasing, or did they just say find the rate of change of the angle? If they just say find the rate of change of the angle, you should put the negative. If they say find the rate of change of angle, which is decreasing, well, they're telling you it's already negative. Just put the answer. Does that make sense? It's an English game. Does this make sense? Did I lose you guys anywhere? Questions? I recorded it so you can go back over it again if you need to. You got another web work problem you like me to do from section 2.7. Number 9? You got it. I'll do it. Number 9. Oh, I did this one in class, dude. Okay. It was actually my problem here. It's diagram situated on page 18, page 312. All right. Well, I'll do it for you if you really want me to. It should take me about 2 minutes. All right. A boat's being pulled into a dock by rings of rope to a pulley on the dock. The rope attached to the front of the boat, which is, okay, this one's changed. It's now, the water's 8 feet above the level of the pulley. Diagram is on page 18 if you want, or you can just watch my video from last class. If the rope is pulled through the pulley at a rate of 20 feet per minute, at what rate will the boat be approaching the dock when 120 feet rope is out? So this was the same problem, and I'm going to go ahead and draw the picture here to remind you guys that we have a dock. Okay? We got some water, and we got our little guy working on the dock here, and he's got himself a nice pulley situation here that he cranks this thing up. And we've got ourselves a boat, and since I'm going to see if you guys actually remember my problem from last time. What kind of boats do I own? That's right. You're going to have a boat, have one with big guns on it. That's right. So we got a battleship, 16-inch guns, and we'll have a radar system so we can find those planes trying to attack us or whatever. All right, and the rope being attached to the front of the boat here. Yeah. Oh, I know. I'm drawing it right now, and then I'm going to switch over. You keep reading the problem. Okay, Z is the hypotenuse. The thing in front of the boat is now 8 feet, and this is X. And what are we supposed to find? dx over dt equals what when 120 feet of rope? Z equals 120 feet. Okay, so just want to show you, I'm just getting all the numbers down here, and it's being pulled through the pulley at 20 feet per minute. Okay, let me switch over. Okay, exact same picture as what I drew last time. I'm trying to make you feel bad about asking me this problem. All right, so here it is. Battleship. Poor seaman 3rd class sitting here on the dock. Okay. Z, there's two. This is constant. This is 8. Things that are changing. When you pull the boat through this, through the string attached to the pulley here, the Z is changing, and they're pulling a rope that's being attached to the front of the boat at a rate of 20 feet per minute. This is your dz over dt. X is the distance the boat is away from the dock, and so we're looking for dx over dt when 120 feet of rope is out. So step 1, read problem, draw a picture, and label it. So I labeled the two variables, x and z, and I know with the information they gave me about pulling the rope through the pulley that the 20 feet per minute is dz over dt, and we're supposed to find dx over dt. Step 1, read problem, draw a picture, label it. Step 2, come up with the equation that you see for this thing. What do you see in this one? I see a nice little right triangle where I know something about all the sides. What does that mean? Pythagorean theorem. So we've got x squared plus 8 squared has got to be equal to z squared. Or 8 squared plus 64 equals z squared in this problem. What am I going to do? I'm going to take the derivative with respect to time of that equation. X squared plus 64 equals z squared. This is going to give me, what's the derivative of x squared with respect to t? 2x what? Very good. dx over dt plus what's the derivative of 64 with respect to t? Being a constant at 0 equals what's the derivative of z squared with respect to t? 2z dz over dt. You with me? What do we want to find? dx over dt. So this is the way I want you to look at it. This is 2x times dx over dt equals 2z times dz over dt. What am I trying to solve for? dx over dt. So that's the guy I'm going to keep as a variable. All these other guys should be numbers or know something about that I can actually plug into my equation so I can solve for that x over dt. Well, what do we know? We know dz over dt is 20, so I can replace the dz over dt with 20. We're supposed to find dx over dt when z equals 120, so z is the 120. What do we know about x? They didn't give me that one, of course. And this is pretty standard. You saw that in the last problem. They'll give you enough information that they may not give you what you need as the variable, but they give you enough information that you can go back and solve for whatever variable was. In the last problem, I had to solve for theta and x. And this problem, I need to solve for this x. So I know z is 120, so x squared plus 64 equals 120 squared. So x squared plus 64 is equal to 120 squared is what? 14,400? Yep. Subtract 64 from both sides. And I get x squared is equal to 14,336. So x is the square root of 14,336, and it'll be a positive square root because x is a positive distance. So I plug it in here, 14,336. So what do I get? I get 2 square roots of 14,336 dx over dt is equal to 2 times 120 times 20 makes it 4,800. And to solve, I'm going to divide by 2 square roots of 14,336. So dx over dt, if you clean it up, 2 goes into 4,800, what, 2,400 times over the square root of 14,336. Or for those people who just love decimals, let's go for it. 2,400, thank you, divided by the square root of 14,336 is 20.04459314. And what would my units be? Being this is dx, x is a distance over d time, feet per, time was measured in minutes in this problem. Does that make sense? Oh, you guys don't believe me. Well, here we go. Proof positive. Let's see here. 20.04459,314 and nothing but UNC Charlotte Green. There you go. Sure. And I will pocket it back up there and do this. You guys can see all aspects of the problem there. You guys happen to have another question? Number 8. Not 18, you want 8. Okay, 8 it is. You guys good on this one? Okay. Number 8. Previous problem. All right, hold on, I didn't mean to do that. Let's see here. 2.7. Number 8. Oh, okay, 8. 8's a good problem. Let's do 8. The altitude of a triangle is increasing at a rate of 3 centimeters per minute, while the area of the triangle is increasing at a rate of 2.5 centimeters per minute. Okay? What is the rate of the base of the triangle changing when the altitude is 10 centimeters and the area is 86 square centimeters? All right, so first thing I'm going to do is I'm going to draw a picture. I'm going to draw an arbitrary triangle. And I'll cut over in just a second, but let me go ahead and draw my arbitrary triangle. Now when it comes to a triangle, the distance between the top point and the bottom side, perpendicular distance, is called the altitude. I'll give it the letter H, and I will give the base of the triangle letter B. And what do they tell me about this one? The altitude of the triangle is increasing, that means it's positive, 3 centimeters per minute. That tells me dH over dt is 3 centimeters per minute. The area of the triangle, area would be big A, dA over dt, the rate of change of the area, is increasing at a rate of 2.5 centimeters squared per minute. What is my question? What is the rate of the base? Rate of the base is the dB over dt equals what? Rate of change of the base when the altitude, which is h, equals 10 centimeters and the area is equal to 86 squared centimeters. All right, so let me switch over and show you what I drew. I have a triangle, arbitrary triangle here. The distance between the top and the bottom side is h for the altitude. The bottom is the base. They told me that the height is increasing, or altitude is increasing at a rate of 3 centimeters per minute, so that's dh over dt. They told me the area of a triangle is increasing at 2.5 centimeters squared per minute. Our goal is to find the rate of change of the base, aka dB over dt, when the height is 10 centimeters and the area is 86 centimeters squared. So I got it all written down. That's what I was doing over here. Does that make sense? You got to come up with an equation for this mess. What are they interested in? They're interested in area. What's the area of a triangle? You got to come up with that one. That's the hard part. 1/2 base times height. Does that make sense? So I'm going to take this equation, area equals 1/2 base times height, and take the derivative with respect to t. Does that make sense? So here we go. What's the derivative of area with respect to t? Well, derivative A would be 1 dA over dt equals, look at this other part, 1/2 base times height. Let's put this together. It's 1/2 base times height. What rule would I have to use to take derivative of 1/2 base times height? Product rule. It's 1/2 base, that's your first function, times height, which is your second function. Product rule, derivative the first times the second plus the first time derivative the second. Derivative the first, what's derivative of 1/2 base? 1/2 is a constant, holds over. What's derivative of b? 1, but every time you take a derivative variable, you got to tack on that dB over dt. This will be the derivative of the first times the second, h, plus the first, 1/2 b, times derivative of the second. What's derivative of h with respect to time? dH over dt. Does that make sense? Did I lose you guys anywhere? Now, plug in what you know and solve for what you don't know. All right, dA over dt was what? 2.5 centimeters squared per minute equals 1/2. dB over dt is what I want to solve for. So dB over dt is when h is equal to 10. So I get to replace h with 10 plus 1/2 b. And dH over dt, they gave that to me to be 3. And all I need is b, and then I can go solve for it. Did they give me b? Of course not. They always give you one short. So what you're going to do is go back to the original equation. Remember, area equals 1/2 base times height. The area they gave me was 86, equals 1/2 the base times the height, which was 10. So 86 equals half of 10 is 5b. Divide by 5 on both sides. b is equal to 86 divided by 5, which is 17.2. Does that make sense? And I get to replug in for b, 17.2. Did I lose you guys anywhere? Now let's do some math. 2.5 is equal to half of 10 is 5 dB over dt plus 1/2 times 17.2 times 3. Let's see what that gives me. 1/2, John, good, times 17.2 times 3 is 25.8. It's arithmetic. Go solve for dB over dt. What you going to do? I'm going to subtract 25.8 from both sides. So 2.5 minus 25.8 is negative 23.3 equals 5 dB over dt. I'm going to divide both sides by 5. This gives me dB over dt is equal to negative 23.3 divided by 5 is negative 4.66, and that would be base is measured in centimeters, time is measured in minutes, and there's my answer. And something you should notice here, with the altitude growing and the area growing, altitude growing at 3 centimeters per minute, and the area growing at 22.5 centimeters squared per minute, the only way you can do this, thing's going to be getting taller, but because the dB over dt is negative, the base is actually getting smaller. It's going negative. Does that make sense? So this would be shrinking as this gets taller. Did I lose you guys anywhere? Questions? Well, I know you people don't believe me, so I will prove it to you by submitting the answer. What did I get here? Negative 4.66. I don't put in units on Wellbrook, and let's see if we get UNC Charlotte Green. Yes, we do. There we go. Does that make sense? Questions? You guys have another one for me to do? Let's see here. Which one? You want me to do number 5? 15. Sorry. 15? All right. Number 15. Number 15 states this. Two sides of a triangle have lengths 10 meters and 12 meters. The angle between them is increasing at a rate of 0.04 radians per minute. You look at that, 0.04 radians per minute. Who's that guy? D theta over dt. How fast is the length of the third side increasing when the area between the sides is fixed at pi third radians, also known as what? 60 degrees. All right, so let me draw a picture over here and label everything. Okay. So this will be side A, this will be side B, this will be theta. Here they tell me d theta over dt is what was it? 0.4? 0.04. I better get that right. 0.04 radians per minute. A, one of your sides was 10. I'll call A 10 meters. And B was 12 meters. Okay? And they're interested in the third side. I'm going to call that guy C. And we want to find dc over dt equals what when the angle theta is pi thirds. All right. If you look at this problem, they give you the hint that, hey, you should use the law of cosines. C squared equals a squared plus b squared minus 2ab cosine of theta. However, you should have known that based upon the fact that you graduated high school, but no one remembers this mess. So let me just tell you what the deal is. Anytime you got an angle, a side, an angle in the middle, and another side. They gave me two sides, and this was the angle in the middle. This is called side angle side of a triangle. With side angle side, you use the law of cosines. Side, 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 if you know all three sides, you use the law of cosines. If you have angle, side, angle, you remember these theorems from your geometry class, or the infamous side, side angle, you're supposed to use the law of sines. Because this was the side angle in the middle side, this is the law of cosine kind of a problem, which they gave it to you. So and I would have too. I'm not expecting you guys to memorize everything. But as you go through math, you begin to see all the stuff we did in high school really come back and haunt you. Law of cosine says that c squared, this side squared, is equal to a squared plus b squared. It's from the Pythagorean theorem. But because this is not a right triangle, it's minus 2ab cosine of the angle between the two. Okay? However, in this problem, there are two variables, theta and c. This angle is moving, and is it increasing or decreasing? I forgot to look, because that's important. The angle between them is, what is that? Increasing. That means it's positive. All right, so go back to the viewer. Thank you. Thank you. All right. So this is a positive because it was increasing. If it was decreasing, it would have been negative. So this thing's getting wider. So if this gets wider, what's going to happen to my c side? It's going to get longer. So you're expecting dc over dt to be positive. All right, but A and B are constants. These guys don't move. A is 10 meters and B was 12 meters, and that's just fixed. So immediately I'm going to plug these numbers in. So c squared equals 10 squared plus 12 squared minus 2 times 10 times 12 times the cosine of theta. Theta is changing, keep that as a variable. So c squared equals, what do we got, 100 plus 144 minus, let's see here, 2 times 12 is 24 times 10 is 240 cosine of theta. So c squared is equal to 244 minus 240 cosine of theta. I went ahead and crunched my constants already. Does that make sense? What am I going to do to this equation? I'm going to take the derivative with respect to time of it. Does that make sense? And when I do, help me out. What's the derivative of c squared with respect to time? Very good. 2c dc over dt equals, what's the derivative of 244? Being a constant, it is 0. What's the derivative of negative 244 times cosine theta? Well, negative 240 is a constant. What's the derivative of cosine of theta? Negative sine theta times d theta over dt. Every time you take a derivative variable, you got to tack on that d variable dt. It comes from the chain rule. Clean this up. I got 2c dc over dt is equal to a positive, negative times negative is positive, 240 sine theta d theta over dt. Now plug in what we want to know. 2 times c, now dc over dt is what we're looking for, equals 240 times the sine of theta and times d theta over dt. We are supposed to find dc over dt when theta is pi thirds, so I replace theta with pi thirds. D theta over dt was given to be a positive 0.04, so I plug him in. And of course, there's all but one of them, you know. You got to go back and solve for that guy. So, I go back to my equation, which is right here. C squared equals 10 squared plus 144, 12 squared minus 240 times a cosine of what was theta being plugged in? Pi thirds. All right, let's see if you guys know it. What's the cosine of pi thirds? Pi thirds is also known as 60 degrees. What's the cosine of pi thirds? Very good, 1/2. Very good. So you get c squared equals 244 minus 240 times a half. So 240 divided by 2 times a half is 120. 244 minus 120 is 124. Sorry, not nice numbers. C squared equals 124. So C equals the square root of 124. And I get to plug him in there. So I'm just going to go for calculator answers here. So this is 2 square roots of 124 equals d times dc over dt is equal to, here we go, 240 times the sine of pi thirds, which happens to be the square root of 3 over 2, but I'm going to go decimals on this thing, times 0.04. And that gives me 8.31384386. Now what am I going to do to solve for dc over dt? I'm going to divide by 2 square roots of 124 on both sides. This gives me dc over dt equals, and watch how I do this. I'm going to hit divide, parentheses, because I got 2 times the square root of 124, close parentheses on that. And I end up getting the answer of 0.3733026101. What would my units be? Trying to get you guys to do it on the test. C is a distance, and that's measured in meters, and time's measured in minutes. This would be meters per minute. Does that make sense? And for those people that don't trust me, shame on you. But let's see here. 0.373303327, 0.3733026101. And we get nothing but UNC Charlotte Green. There you go. Hope this was helpful. Study more hard on this one. And I'll see you guys tomorrow. And if you want to turn in your papers early, you can turn them into Katrina in the back. See you guys then.